Welcome at Eindhoven University of Technology. Normally this campus would be crowded with 15,000 students, but due to COVID-19, unfortunately, it's empty. And it's the reason that we cannot meet in person here at our campus, which is a pity, of course. At Eindhoven University of Technology, we develop new knowledge related to the issue matter of digital concrete. Sometimes in isolation for fundamental research, but in this brainport region of Eindhoven, most of the time in close collaboration with our industrial partners. Eventually, all the knowledge that we develop should end up with the industry for reasons of construction productivity, more sustainability, and a larger degree of freedom in architectural design. Today, we're going to visit a unique project in the eastern part of the Netherlands.
Right now we're in Teugen, near the small airport of Teugen, where local business owners Arvid and Mario wanted a small, circular meeting room. One of the requirements of the client was that it should be possible to project images and videos on each wall surrounding the meeting room to change the mood of the meeting room. My name is Marijn Bruurs. I'm working at Witteveen & Bos, a large design and engineering consultancy in the Netherlands. We are with around 1,300 people globally in offices all around the world. We work on different types of projects, coastal defense projects, port projects, infrastructure projects, but also in the built environment, in which we're also involved in 3D concrete printing. We've been involved in many 3D concrete printing projects around the world, one of which is the R&D Drone laboratory in Dubai. And we operate the largest gantry printer in Southeast Asia with our team in Singapore. Other projects we've been working on include bridges in Gemert and in Nijmegen, and soon to be built bridges in North-Holland. We got into digital concrete because we need to increase the productivity of the construction industry. There's still too many people needed to build infrastructure, to build buildings around the world, and those people are not available anymore and don't want to work in construction anymore. That's why we need to make it more appealing for young people like me to work in construction. The second reason is sustainability. The construction industry is responsible for around 40% of CO2 emissions around the world. With digital concrete, we can use smarter materials and we can use less material. In 2016, Arvid and Mario challenged the construction industry to come up with innovative ways to construct their dream. Multiple companies took on this challenge to create this special building. We started a collaboration with the contractor, Witteveen & Bos for the design and the engineering, and Hugo de Jager of Revelating to be the project manager. Together we took on the challenge to 3D print the first load-bearing, approved 3D concrete printed structure in the world. Architect Pim van Wielik of the Form Foundation designed this meeting room in such a way that from the sky it looks like a vortex created by an airplane. This is why all the walls in this meeting room are double curved. With the freedom of shape that 3D concrete printing offers, the architects started designing. But soon we realized that there were not unlimited possibilities in the design of 3D concrete printed buildings. So we needed to change the design to make it printable and make it work structurally. So we had multiple sessions with the 3D printing company, with us as the structural designers and the architect to create something which is both unique, feasible and structurally sound. The foundation of the building is a hectare flooring which is ideal for thermal insulation. On top of the hectare foundation, we started printing walls. These walls were printed on site in a big tent to prevent the influence of the climate on the printing process. Each wall consists out of 4 layers of printed concrete. 3 layers form an inner part, which is the structural part, and then there's an outer shelf on the outside, creating some visual effect on the outside. The outer leaf of the wall is connected to the structural part of the wall by wall ties, which were specially designed and tested for this project. Printing one wall element of about 3 meters in width took around 2 hours. When the printing was completed, the lower 30 centimeters of each wall was filled with cast in situ concrete to create a connection between the foundation slab and the wall. On top of the beam connecting the wall element to the foundation, biofoam was injected into the walls to create a thermal insulation. Biofoam is a biodegradable insulation material which can be reused when the building is demolished. On top of this biofoam, a concrete beam on top was cast to create a connection to the timber roof structure. When we started with this project in 2016, there was only one commercial 3D printer available in the Netherlands that could print on-site. This printer consists out of an ABB robotic arm, which is placed onto a mobile platform. Because of this platform, the printer is able to move around the construction site. It cannot move around the construction site and print at the same time, so each wall had to be divided into different wall elements which the printer could reach from a static position. The advantage of this printing system is that it can be used on-site, and when it's on-site, it's easy to maneuver around the building site. The disadvantage of this type of 3D concrete printer is that moving it around the construction site takes quite a lot of time. For example, here in Eindhoven, printing one wall element takes around 2 hours, but moving the printer from one place to the other place takes around 6 hours, including, of course, calibration of the robot. Besides 3D concrete printing, we also used other digital technologies for this project. The shape of this project is so complicated that it cannot be drawn into a simple 2D model, which is why we needed to create a parametric 3D model of the entire building to understand its complexity and to understand the shape of the building. Besides the parametric modeling, we also used finite element software to analyze the structural behavior of the building and to understand the flow of forces during the tests. In order to obtain a building permit, we had to go through a process of design by testing because there's no Eurocodes for 3D concrete printing. What we did was we printed one wall element on a 1:1 scale in the factory, which was tested until it failed. Eventually we did not get up to failure because the testing facility could not reach the ultimate failure load. By using design by testing with 1:1 lab tests together with advanced finite element modeling, we were able to convince the local government to give a permit for this building in which it is allowed to use the 3D concrete printed walls as load-bearing structural walls. We tested the wall both for the vertical loading as well as the horizontal loading caused by the wind, by pushing the walls towards the inside but also to the outside in multiple cycles to see if it would fail. Design by testing is of course a lot of fun as a structural engineer, but looking towards the future of 3D printing in construction, we should not use design by testing with big 1:1 lab tests for each project. We should look around the world to see which tests have already been performed, which tests were successful and can be implemented into your own project. Because it's the first time we've 3D printed a concrete building in which the 3D printed concrete is also used structurally, we of course have to check the long-term behavior of the material in time. At this moment, we're only observing small shrinkage cracks in the finishing of the wall elements, which is not disturbing for us as structural engineers. One of the things we've learned in this project is that the 3D printed mortar which we have used for this project reacts with the cast in situ concrete, which creates a dark brown finish on the outside of the printed walls, which was not intended in the design. Another thing we learned was that it's difficult to print with a fast hardening mortar outside, which created cracks during printing in some of the wall elements, which then had to be redone. Another learning point in this project was that with 3D concrete printing, it's important to have a digital workflow. In this project, the designers, the architects, the engineers worked in a parametric model and the contractor worked in another model, which created some slight changes in the as-built model compared to the design model. The future of 3D concrete printing is the future of digital construction, which means we need to increase the productivity on the construction site and we need to work on the sustainability of construction. Working on the productivity of 3D concrete printing means that it should be easier to operate printers on site, and the printers that are available should be more robust. Working on the sustainability means foremost working on the material. The materials that we use nowadays for 3D concrete printing contain a lot of Portland cement, which ruins the sustainability of most 3D concrete printed projects. My question to you, scientists and researchers from all over the world, would be to develop a more sustainable material for printing. As structural engineers, we can reduce, with 3D concrete printing, the material we use in projects by over 70%, but if we still print with Portland cement, we will never meet our sustainability goals. So please work on more sustainable, printable mixtures. 3D concrete printing is only one step in the construction process. We need the robot to take over the site, and we need you to put the robot to work.
Yeah.